This is Lab 3, Mass of a Black Hole. The purpose of this lab is to analyze the motion of objects around the black hole to estimate its mass and figure out the initial velocity needed to allow a ship to escape the system. In this lab, there were two models created, the star and black hole model and the planet, ship, and black hole model. Both are coded in GlowScript. The most prevalent physical principles present in this lab is curving motion, more specifically the concepts of the parallel net force and the perpendicular net force, gravity, the momentum principle, and Newton's second law. The main result of this lab was that the black hole had a mass of 1.1821 times 10 to the 35 kilograms, and the ship needed an initial velocity of -1 times 10 to the 8 meters per second in the x direction and 1 times 10 to the 7th in the y direction to escape the system. This is about 1/3 of the speed of light. One of the main physical principles in this lab is curving motion. In curving motion, the net force is equal to the force in the parallel direction plus the force in the perpendicular direction. The force in the parallel direction is the change in the magnitude of momentum over time, and it's in the same direction as the momentum. The force in the perpendicular direction is the change in the direction of the momentum over time times the magnitude of the momentum. The force of gravity can be found by multiplying -g times the mass of the two objects in question and then dividing by the magnitude of the squared distance between them. The force is in the opposite direction of the position vector between the objects. The momentum principle and Newton's second law state that the momentum is equal to the net force applied over time. Although the equations look different, they are essentially the same thing. The principle of curving motion was used to figure out the net force in the system, which was then used to calculate the mass of the black hole using the gravity equation. The momentum principle and Newton's second law was then used to iteratively predict the motion of the objects in the model. In Model 1, the system was the star, and the surroundings were the black hole in the universe. The planet had an initial position of 3.8 times 10 to the 12 meters in the x direction and 2 times 10 to the 12 meters in the y direction. The initial velocity is not known. The net force was calculated using the momentum principle, which was then used to calculate the parallel and perpendicular forces, allowing us to see the motion of the object. The net force was also used to calculate the black hole's mass by rearranging the equation for the gravitational force and plugging in the values for the variables as seen in line 197. The black hole's mass was 1.1821 times 10 to the 35 kilograms. This is the result. The mass I found was the average of all the masses calculated. In Model 2, the system was a ship, and the surroundings were the planet, the black hole, and the universe. The ship had an initial velocity of -1 times 10 to the 8th meters per second in the x direction, and 1 times 10 to the 7th meters per second in the y direction. It had an initial position of 1 times 10 to the 10th meters in the x direction, and 1 times 10 to the 8th meters in the y direction. The position vectors between objects, along with the gravitational forces between them, was calculated. The black hole's mass for Model 1 was used. Newton's second law and the position update formula was used to make objects move, and the initial velocity of the planet was found using a guess and check method. The first successful initial velocity that allowed the ship to get close to the black hole and escape the system was the velocity given. This is the result of Model 2. Because there is no experimental portion and the model is our data, there are no similarities, differences, or sources of error. Although the rate of change in momentum and the net force are related to each other and often are the same vector, they are technically different things. The rate of change in momentum is calculated directly through an object's motion through the change in instantaneous velocity over time. However, the net force is calculated by adding all the forces acting on an object at a time. So, for example, although the rate of change in momentum is affected by gravity, you don't need to know the actual force to calculate it. However, you do need it to calculate the net force. For the ship to be in orbit around the black hole, the speed needs to be low enough to not be able to escape the black hole's gravitational force. And initial velocity that makes this happen is 1 times 10 to the 6 meters per second in both the x and y direction. Thank you for watching my video and have a great day.